All right, welcome everyone. Nice to be here. My name is not Caius, that's Caius, but I get the pleasure of introducing him. Etleap is a tool for ingesting and modeling data for lake houses, basically, in the cloud. We take all the effort out of building and maintaining data pipelines. So we don't get to talk about the internals of our product very often. So really excited to be here with a group of people that might actually find this as interesting as we do. We're going to share the details of basically how we built our platform to support data ingestion at scale for Iceberg. Etleap supports many data sources. The most popular data source type that we have is SQL databases. And over the years, our customers have had many feature requests for our SQL database source support. But two have really stood out. The first one is about latency. So how can I get my data ingestion latency down to a handful of seconds instead of minutes? This can help unlock near real-time use cases, like operational dashboards, for example. Now, another is, let's say I'm ingesting my data into my data warehouse, but as my company grows, I'm starting to use other data platforms as well. It's very common to have both Snowflake and Databricks, for example. And when you do, wouldn't it be better to have a single set of data ingestion pipelines rather than two sets of ingestion pipelines? So those have been pretty common requests. And it turns out that Iceberg is actually a big part of the solution, or a solution, to both of those challenges. So very excited to be telling you about it today. And if you like what you hear and you'd like to try out Etleap for your data pipelines, come talk to us at our table. It's basically right outside the door to the right. And if you are an engineer and you are really into Iceberg and you want to come help us build the next generation of data infrastructure, come and talk to us as well. We are hiring for our SF-based team that is 5 blocks from here, right down the street. And with that, I'll hand it over to Caius. Thank you.
All right. Thank you, Christian, for the intro. So my name is Caius. I work with Etleap. And today I'm going to talk to you a bit on how we work with Iceberg. But first, before we get started, let's look a bit at what we're going to cover. So I know this looks like a lot. I promise it's all bite-sized and it's going to go through quickly. We're going to look through our Etleap kind of batch architecture, what were the challenges. We're going to look at what Iceberg brings, and we're going to look at Apache Flink, an intro, and kind of how we made it work. And then we're going to look at our new architecture, and then we're also going to cover a bit how we integrate with warehouses. We're going to do a demo, and then we're also going to talk about an exciting use case that we found internally at Etleap. So to get us started, let's look at our batch architecture. So let's say you are Acme Corporation and you want to move your data to your warehouse or your data lake. And to do that, you create an Etleap pipeline, data moves over, it's all good. But what exactly happens under the hood? So what happens under the hood is that we use AWS TMS, Database Migration Service. And in the case of Postgres, it will read the write-ahead logs from the database, and then it will write those to S3. There, we will batch them, and then we'll use EMR to process the data. We will stage the data back in S3, and from there, we will load it either into the warehouse or into the data lake. And one trivial approach to make this faster is to make the batches smaller and run more frequently. However, we found out that doesn't scale. And it doesn't scale for a couple of reasons. So first of all, warehouse ingestion is slow. And by that, I mean we need to stage data to S3. We can't stream, usually we can't stream data directly into, so we need to stage data to S3. So we need to write it, we need to read it. That adds latency. Loading requires a merge operation, right? Whenever we want to update existing rows, we have to merge the data into the existing table. And if it's a really large table, that can take a while. And then finally, there's also limited resources. We have found that with a large number of pipelines that load very frequently, eventually we end up being throttled by the warehouse because we don't have enough resources to kind of do the loads of the performance that we want. And then on the other side, looking at data lakes, we also have limitations. If the batches are really frequent and the files are too small, this will add a lot of overhead when we query data in the destination, right, using our analytical engine. And also, for data lakes in particular, road updates are actually very hard because data lakes are append-only destinations, right? It's very easy to add a row, and if you want to update an existing row, you actually have two options. First is you derive it at runtime via SQL, which can mean that you have very slow queries, right? Because if you have a really large table, you have to scan the whole table. Or, and we do offer this option in the product, is we compute the latest version for each batch. So as soon as we load a batch, we read the table and we figure out what's the latest version, and then we rewrite the whole table. And again, this adds a lot of slow, so you end up with high latency. And for context, what I mean by latency here is that how far the data in the destination is from the source, right? So I referred to this multiple times during the talk. And then high latency means your data is more out of date, bad things happen. So in order to we looked at Apache Flink, and that allows us to kind of solve those problems. And in order to make ingestion fast and efficient, we decided to use Apache Flink, right? That's kind of the ingestion engine that we kind of built our streaming architecture on. So, but just a very brief intro for Apache Flink. For those of you who don't know, Apache Flink is an open source. It's a distributed stream processing framework. It's been around for a while. It's really great. It's also very high performance, scalable, and low latency. This is something that was kind of core, it was a core feature set for what we're looking for. And also it handles both, near real-time and batch data streams. While we have a lot of, new stream use cases, we also have a lot of, legacy sources that might use batch, and this is great since it can support both of them natively. So here are some of the key features that when we made the decision that we looked for. First of all, it has native Stream and Iceberg support. Because of that, that kind of simplifies our development process and also has really great integration, and it's also very well documented, which is great. Also, Flink allows us applying arbitrary transformations in transit. As Christian mentioned before, we are an ETL and ELT company. The T happens before we load, and then with Flink, it allows us to kind of define those transformations in a nice, convenient way. And then finally, it has built-in constructs to ensure atomistic and data integrity. And this is kind of the key feature that kind of allowed us to make this decision. And in particular, it's checkpointing and exactly once guarantees. And this is something I kind of want to go over with because it's kind of key to understanding how Etleap pipelines work and also why we are able to guarantee really high data availability and also perfect accuracy effectively at the end. So exactly once processing, like I said, it means 100% data integrity. That means that if I put a row in the database, I want to see it in my destination exactly once, not more, not less, because if anything is mismatched, then I have a problem. So this applies to anything that's like external state, anything that happens outside of the pipelines. And that's not only the data processed as part of the pipeline, but also our own internal statistics and metrics. As part of the pipeline, we have monitoring and observability. We report a lot of statistics to the user, which we're going to see later in the demo, and we want those to be as accurate as possible. So Flink's built-in checkpoint mechanism was what enabled us, and we had to by leveraging it and being very careful on how we defined our pipelines, we were able to kind of guarantee this end-to-end. So how does checkpointing in Flink work? So first off, up here we have the job manager. That's the Flink job manager that kind of orchestrates the whole thing. This is a very simplified picture of our data pipeline. So let's say we have Kinesis as a source. It goes through the data pipeline, writes into Iceberg. We have source, sync, and we have a bunch of operators where we define transformations. And then we also have S3, right? And that's going to serve as durable storage. So normally data goes through just fine, and then every now and then we're going to go to when this happens, Flink uses what we call a two-phase commit, right? So there's a phase 1 and a phase 2. Being interrupted at any point is fine, and we're able to always recover just nice. Phase one, the job manager says, I'm going to introduce a bearer into the stream. So what this happens is that whenever an operator sees this bearer, it's going to save its state to S3, right? So it's going to go say, it's going to look at the data that it has, it's going to snapshot its state, and it's going to write that to S3, and it's going to do that before it processes any data that goes that's behind the barrier, which means is that if anything goes wrong, I can always load that saved state, and I can load it into the operator and process data afterwards and know that it is that I'll be consistent. And then it kind of passes this operator along, and it goes through, goes through the entire pipeline at the end. And then once it goes into the sync, it means that everybody has done their checkpoint, and it basically lets the job manager know as saying, hey, everybody has checkpointed, everybody saved their state into durable storage. None of this is still visible externally yet, by the way. So all of this happens internally. We can go on and we move to phase two. Once phase two happens, the job manager tells everybody saying, okay, checkpoint is complete. Go ahead and do your commits, right? This is the commit phase. This is where anything external happens. So it is at this point that we actually commit the data to Iceberg. So now we have the data files that were previously written during the pre-commit phase. Those are written to S3. We generate new metadata files, and at this point we also update the external data catalog. So it's after this point that data can be visible by consumers if you query the table. It's also crucially important that this phase is idempotent, right? If something happens right now, we have to be able to basically commit again and make sure we have the same result. And this applies not only to our Iceberg data, but also applies to our statistics and metrics. It is during this phase that we take the statistics and metrics we computed, and we send that back to our application for reporting visibility to the user. And again, this has to be idempotent to make sure that we report accurate metrics. Okay, so of course the question is how often should you checkpoint, right? Because it's, as I mentioned before, it's only at the end of the second phase is that the data is visible to the consumers. So if you do it so you might be tempted to do this, for example, very frequently, right? Let's say, okay, I'm going to do it as frequently as I can. However, this has overhead because for the brief period that the first phase happens, that we take those checkpoints and we sort them to S3, there's a brief interruption in the data processing. If you do it too frequently, you end up having more time spent checkpointing than doing actual work. So your overheads become, more than it's worth. And also, again, if you do it too infrequently, it means that data will actually be visible to the external users of Iceberg less frequently, which ends up high latency, right? The data will always be a lot less far behind because I have to wait for a checkpoint to come around so I can see new data. And for our use case, this is not what I wanted. There we go. Push the wrong button. For our use case, we found that 3 seconds is the current balance. Our goal was to have 5 seconds or less. We found that 3 seconds, we have a consistent, the data is visible, and also overheads are fairly minimal. And then also let's look at a few tips and tricks that we found for checkpointing. And I said, because it is such a critical operation, like we really want to do the minimum amount of work during checkpointing. So during development, we really paid a lot of attention into measuring and making sure that we did the minimum amount of checkpointing, and any code paths that were around this were extremely optimal. And also one side effect that we found is actually the number of Iceberg snapshots in your metadata actually affects the checkpoint duration. So this is something that we had to consider, and is something like as part of the pipeline maintenance we maintain and we clean. So with this in mind, now that we've kind of gone through, let's look at Etleap streaming architecture and let's see how all of this kind of plays in. So we're going to start with the same scenario that we had before. We have our fictional corporation, Acme Corporation, and they want to take data from database to Iceberg, right? They set up a pipeline, everything works well. What happens under the hood? Well, so as before, we start with DMS, Database Migration Service, that reads the write-ahead logs, reads any transactions. And then, instead of writing data to S3, we write it to Kinesis. At this point, it's immediately picked up by our EMR cluster. And then that data gets written to Iceberg through the process that we've seen. And once the data is in Iceberg, you can go ahead and you can query it, either directly through, for example, Athena, or you can use, Redshift, Snowflake, Dremio, and any kind of warehouse that you want. And speaking about warehouse integrations, this is also something that we kind of put a lot of thought in. And, it's great because if you have Iceberg as a data source, and then a warehouse, you unified the data lake and the warehouse, so you're able to query data across both of them. And then data stored in S3 externally means it's cheap. We all know S3 is cheap up to a certain extent, but cheaper than the warehouse. And then we store metadata in a data catalog like AWS Glue. Now you can take all of these pieces and you can handle them yourself, right? But we kind of do this for you end to end, right? So like once you have in Etleap, you can configure saying, hey, I want this data to be available in this data warehouse. So not only do we write the data to Iceberg, we also set up. So I'm going to use Snowflake as an example here. In Snowflake, we need to have an external catalog, we need to have an external table, and we need to have all of that set up. All of that wiring is done as part of the setup, but also we periodically refresh the metadata, right? For Snowflake, we have to periodically refresh the metadata, and what we're doing is that we're actually doing this during the checkpoint phase. So after the data is committed to Iceberg, I know that it's visible to external consumers. I can go ahead and trigger a refresh, which makes sure that the data that's actually visible to Snowflake is as frequent as possible. It's as fresh as possible. And we're going to see kind of the side effect of this once we go into the demo. So yeah, here we are at the demo. This is the most interesting part. So I'm going to go hide behind my laptop. So if you have gone by our booth, by our table outside, you might have seen this screen, right? It basically shows us that it is, we're getting data. So in this case, we are getting data from a Postgres data source into Iceberg, and we're currently using Snowflake. And you can see kind of the results of the queries live there, and we are getting under 5 seconds. And also the table size that we're updating is not a trivial table. It's about 1.1 billion rows. So it's a pretty large table that we're doing it in pretty much near real time. So this behind all of this is an Etleap pipeline. So here I have the pipeline. So I know there's a lot going here, so I'm just going to walk you through kind of the main key concepts that we have. So here on the left, we have data for the past hour. So you can see we have the pipeline. This is the pipeline latency as it's been measured and has been reported by our Flink job continuously. And you can see that's always consistently under 5 seconds. And then here we can see the number of rows ingested. So there is some activity. This isn't a static example. We have about 32,000 updates an hour, which is only 8 seconds, or about 8 or so updates a second. Our design goal when we built this was to have 10,000 inserts, updates, or deletes a second. And this is something we successfully achieved in production pipelines without any need of significant optimizations to do that. So moving on to the last part of the demo is like, what does this feel like? What are kind of the implications of having data this fresh? So to do this, I'm going to need a bit of audience participation. So what I'm going to do is I'm going to take data, I'm going to insert it into an Postgres table, and then we're going to query it in Snowflake after 5 seconds, and we're going to see it updated. So I'm going to need one of you to give me your name and your favorite book. So I'm going to switch here. I'm going to here I have the first tab is the Snowflake, and the second tab is the warehouse. So yes.
Ravi, designing data intensive.
Ravi. And I'm sorry, what's the book name? Designing?
Data intensive.
Oh, okay, I need
Just say data intensive.
data
Intensive.
intensive. Oh, come on, I can do it. There we go. Okay. Live typing. This is always the hardest part of a demo. Okay. So what I'm going to do here, I'm going to put this is a time sensitive, so I'm going to put the microphone down. But I'm going to insert it here. I'm going to make sure that it goes through. And then hopefully by the time I get to switch over, we're going to see it work. So here we go. So inserted. So we can see that it's there. And then hopefully by the time I switch the demo and I spend some time to give us a good chance of success, it is... There it is, 5 seconds, right? So what this means is that really the team that's doing analytics no longer has to worry about data freshness because it's always there, it's always fresh. And also, what you didn't see is what I didn't do. I didn't have to worry about external tables. I didn't have to worry about updating metadata, refreshing tables. All of that was done as part of the Etleap pipeline so that I could figure out, just work on the query. So all of that extra, accounting work that might happen is kind of taken care of. So, okay, and then I will go back to the slides, and then we're going to go over the last point that I have, which is using Iceberg at Etleap. So what we found is that Iceberg is a great solution, but it's not just for really big data sets. So one kind of aspect of our data flow is that we can actually write out arbitrary outsized outputs that shouldn't go into the destination table. And a very common use case of this is records that are invalid. So for example, let's say you have a string value in a column that's supposed to be a number. What happens in this case is that we quarantine the data. So any bad data that, for example, doesn't match the type check is quarantined separately, so that it can be analyzed and kind of inspected and handled with later, while good data still goes into your destination. And we also, because the goal is for the user to look at this data, we need to retrieve these records and show them to a user at a later date. So before Iceberg, we basically stored the rows of bad value in S3 files, what I call loose files. However, this presented a problem when we needed to show the data to the user, because if it was a big file, we had to read the entire file. There was a lot of I/O. That's the problem. And also, we had to do a lot of filtering and displaying the data, because this ended up in the front end, and there were limitations to how much data we could send out. And ideally, what we really wanted would be a fully structured approach where we could just say, give me bad row since a particular date. And what we found is that Iceberg is actually the really perfect solution for this, because it is a structured format, and it is just, air quotes, really strong air quotes here, it is just files in S3, right? So we don't have to pay a lot. It gives us consistent query times if we get the partitioning right? We figure out a partitioning scheme that allows us to kind of give us constant query times that are compatible with a kind of an online operation where you click, show me the bad records, and then it returns them back. And also, because of Iceberg's features like hidden partitioning and schema evolution, we're able to evolve the schema partitioning as we go along, and this has really helped our development process. We can kind of be really fast and agile, and Iceberg can kind of keep up with us and allow us to be that way. So what are the conclusions for this talk? Is that in our opinion, Iceberg is the future of data lakes, because it is a structured format, and we can easily query and integrate it with any other analytical engine you might use in your company. And then at Leap, we really want to help you and unlock its full potential. We do seamless ingestion, we do automated maintenance, adaptive schema evolution, and we also optimize your tables behind the hood for performance and scalability, so you don't have to worry about all of the dirty nitty-gritty details. Our goal is for your team to focus on delivering insights while we handle the heavy lifting behind the hood. So yeah, if you haven't seen us already, please come see us at the Etleap table. We're just over here on the right, and it looks like we have 2 more minutes. So, what did I do? I have no idea. Can I do escape? So yeah, come see us at the Etleap table, and thank you very much. And we have 2 minutes, like we can take one question. And for anybody else, please.
Actually, I have 2 questions.
What happens when you are doing the initial seeding process? That's one part of the question. The other part of the question is you're doing 3 minutes like freshness, which inherently will generate small files on Iceberg side. So how is that part of the maintenance being handled?
So to answer the first question, so as part of the initial setup, we actually will use extractions to extract the data from the data pipeline, from the table. So we do that as fast as possible, and then we basically put those records on a Flink stream, and they're processed. So that's usually pretty fast. And on the second point, there is a separate maintenance process that we run as part of pipeline operation that compacts and kind of handles that under the hood that we didn't go over.
How is the confliction resolution being handled during the maintenance part of the work versus the continuous ingestion you have?
I don't think I can answer that right now, but we can talk about it at the booth because it's a bit longer. So yeah, so if anybody has any questions, please join us at the end at our table just here to the right.